Hello, guys. This simple-looking semicircle problem is from a Japanese high school entrance exam, and it has a beautiful, elegant trick to solve it. Do you think you can spot it? We have a semicircle with a radius of 6. A line is drawn from one end point of the diameter to the circumference, forming a 30-degree angle. We'll call the midpoint of this line M. Another line connects M to the other end of the diameter. This creates a closed shape, and our goal is to find its area. If you'd like to try solving this yourself, pause the video now. All right, let's break it down. To solve this, we'll need to remember the properties of isosceles triangles and a clever rule about parallel lines. First, let's draw a line connecting the center of the semicircle, O, to the point C on the circumference. Since OC is a radius, its length is 6. We are given that the angle CAO is 30 degrees. Because both OA and OC are radii of the semicircle, they are equal in length. This means that triangle AOC is an isosceles triangle. In an isosceles triangle, the angles opposite the equal sides are also equal, so angle ACO is also 30 degrees. Now, we can easily find the angle AOC. The sum of angles in a triangle is 180 degrees, so angle AOC is 180 minus 30 plus 30, which equals 120 degrees. Since the diameter of the semicircle is a straight line, the angle along it is 180 degrees. Therefore, we can find the angle COB by subtracting angle AOC from 180 degrees, which gives us 60 degrees. Next, let's look at triangle OCB. Since both OC and OB are radii, they have the same length of 6. This makes triangle OCB an isosceles triangle. But wait, one of its angles is 60 degrees. This means the other two angles must also be 60 degrees, making it a perfect equilateral triangle. Now, for the brilliant part, how do we find the area of our strange target shape? Calculating the area of the triangle part and the curved arc part separately would be very difficult. This is a classic sign that we shouldn't calculate it directly, but instead transform it into a simpler shape. This is where point M becomes important. Let's draw a line connecting the center, O, to the midpoint, M. Now, think back to the midpoint theorem. In the large triangle ACB, since O is the midpoint of the base AB and M is the midpoint of the side AC, the line connecting them, OM, must be parallel to the third side BC. This is the key to the entire problem. When you have two parallel lines, any triangle with its base on one line and its vertex on the other will have the same area. Let's look at triangle MCB and triangle OCB. They share the exact same base, the line segment CB. The third vertex of one triangle is M. The third vertex of the other is O. Since M and O are on a line that is parallel to the base BC, both triangles must have the exact same height. Since they have the same base and same height, the area of triangle MCB is exactly equal to the area of triangle OCB. So, let's go back to our original goal, to find the area of the shape bounded by MB, BC, and the arc of the circle CM. Let's take the substitution back to area of triangle MCB plus the circular segment of CB. We can replace area of triangle MCB with the equal area of triangle OCB. So, area of triangle OCB plus the area of the circular segment of CB equals the area of the sector OCB. This is a perfect simplification. The complex shape has the exact same area as the simple sector OCB. We know the radius of this sector is 6, and its angle is 60 degrees. The formula for the area of a sector is n divided by 360 times pi times r squared, where n is the angle and r is the radius. Plugging in our values, we get 60 divided by 360 times pi times 6 squared. This simplifies to 1 over 6 times pi times 36. The 6 and 36 cancel out, leaving us with an area of 6 pi. So the area of that complex shape is exactly 6 pi. The key was transforming the shape. We replaced the area of triangle MCB with the equal area of triangle OCB, and this swap made the problem incredibly simple. I hope you enjoyed this problem. If you found this video helpful, please give it a thumbs up, and don't forget to subscribe for more math videos. Thanks for watching.